Hi everybody, today we're going to be talking about kinetics and equilibrium, specifically kinetics. What in the world is kinetics? Well, kinetics is all, when we talk about kinetics, you should know by now, it's all about speed. It's all about motion. Okay, so as we think about kinetic energy is energy of motion, and we're going to talk about some speed. So when you think about a rate of speed, if you think about runners, you might think about meters per second. If you think about cars, you might think about miles per hour. All right, so all of these are legitimate ways to measure speed. And you'll notice it's all distance divided by time. So that is what we're going to focus on, is a rate of speed of how fast something is going. And of course, we're talking about chemistry, so we're talking about the rate of speed of molecules. So how fast does a reaction happen? Well, if you look at cookies, it might take you, let's say, 7 minutes to make some cookies. All right. Whereas if you make brownies, it might take you 28 minutes for those to bake. Whereas if you're making turkey might take 3 to 4 hours to bake. Okay. So when you're looking at reaction rates are different based upon the thing that is reacting. Okay. So let's look, for example, chemically at a description of what might happen for a decomposition of red squares. So you start with all red squares, and at the end, you've only got, in this case, 1. Maybe it'll eventually get down to 0. Right? So the reaction rate or rate of chemical change is usually expressed as the amount of reactant changing, kind of like the runner doing distance, but it's the rate of the reactant changing per, of course, time. So it's the concentration of our stuff over time. So if I look at time 0, I've got all of these red squares over here. But let's say this is minutes. Okay, at the end of 30 minutes, you've got very, very few red things left, and they're almost all blue. So the reaction has almost gone to completion. Okay, now whether this is minutes, hours, seconds, I really don't care. The whole purpose is, as we look at the reaction going left to right, we are decomposing the red squares into blue circles. So we certainly could do that with some other, some chemical that was going on, right? Let's think about how we take a reaction, in this case of fire burning, how do we take this reaction and slow it down? How do we speed it up? Well, what kind of things can you think of? Pause the video. What kind of things can you think of that would slow this reaction down or that would speed it up? Well, of course, the most obvious way to slow it down is pour water on it. That's what fire trucks do, of course. And for those of you who don't know this, that doesn't smother the fire. What that does is it cools it off. So the whole concept of water's cold. For wood to burn, it has to be at 451 degrees Fahrenheit. For those of you who know the book Fahrenheit 451. So you slow it down by making it colder. How do we speed it up? Well, certainly we could add more heat to it. We could add more air to it. We could go and start this fire in when there's a lot more wind, and that would make it go faster. All right, so let's look at some of the factors that we can use to affect reaction rates. We've already talked about a couple. You could make it hotter, which will make something react faster, usually. We make it colder. That'll make it react slower. The concentration. We could change the concentration of stuff that we're working with so the molecules bang together more frequently, and so the reaction would actually happen faster. Right? If you think of putting a lot of sugar versus a little bit of sugar in water, the more sugar it is, the faster it dissolves. Okay? The particle size. Well, let's face it, if you want to start a fire, you use small pieces of wood. Use kindling. You don't use big logs. Okay? So the things that are smaller will react faster. They have more surface area. The things that are bigger will react slower. Right? Activation energy. You could lower the energy with which it takes to start something. Okay, for example, a match is an example where that makes it easier to light a fire versus having 2 sticks to rub together. Okay, so we're going to talk about all of these chemically to see how they work chemically. right? When you think of milk and you put milk in the refrigerator, why do we do that? Well, we do that because cold slows down most reactions, which in our case is bacteria formation. So we're hoping that it happens slower. So we don't leave the milk sitting out on the counter, right? Because heat speeds up most reactions, which is the bacteria forming. Now, why is this? Why does cold slow down most reactions and heat speed up most reactions? Well, chemically, what's happening is the molecules are hitting each other more if it's hot. Why? Because they have more kinetic energy. They are moving faster, right? So they collide more frequently and they collide with more energy. And we talked about that in our last podcast. So that's why heat speeds up most reactions. The molecules hit harder, they hit more often. How about concentration? Well, if we take a wooden splint, which is almost out, it's still hot, but it's almost out, and we put it in pure oxygen, well, then the wooden splint will come back to life and it will start to burn some more, right? And this is because when you put something in oxygen, oxygen is required for something to burn, and if you add a lot of oxygen, then it burns faster because there are more oxygen molecules hitting the part of the thing that's hot. Okay. We discovered this in the United States back when the Apollo moon shots first started back in the 60s, and I guess it would have been the 60s, I think. Anyway, when they did Apollo 1, they had filled the capsule with pure oxygen, just so that the guys could breathe it easier. Well, the problem is that pure oxygen, there was a spark somewhere inside the capsule, and because pure oxygen promotes burning a lot, everything inside the capsule started to burn. Okay, and when it started to burn, they couldn't get the astronauts out quickly enough, and so they perished in the fire. But the point here is they used pure oxygen inside the capsule, so that made the fire happen faster. That fire never would have happened if they'd had a normal atmosphere in there, which, by the way, they eventually went to. Particle size. All right, look at these logs. They're 2 feet in diameter, let's say. All right, are you going to go and take this log and put a match under it and start it burning? Of course not. You need to start with smaller pieces of wood. You need to start with kindling to get it going. Okay. Now, eventually, you could put this log on the fire, right? If you made the fire big enough, kind of like that bonfire we saw a couple slides ago, right? So, you certainly can burn this wood, but you're not going to start it with just a match. Okay. So, particle size is important. You need to burn the kindling first. So, what I'd like you to do here is I'm going to run through these definitions, and you should pause the video and write them down. The activation energy is the minimum energy colliding particles must have to react. And I'm going to show you a picture of this in a minute. But when particles collide, they have to have a certain amount of energy for them to react. And that's the minimum energy, and that's the activation energy. Now, when they're trying to react, when they are together, they form something called an activated complex, which is an unstable arrangement of atoms that form momentarily at the peak of the activation energy barrier. In other words, when they're transitioning from one thing to another, when they're transitioning from the old thing to the new thing. And then enthalpy, we've talked about all of these before. Excuse me, enthalpy is the energy released or absorbed by a reaction. And we refer to that as delta H. So pause the video, write all those down. Okay, and now we're going to look at a graph that shows us those things. We have some reactants over here, and we are producing over here products, right? And in this particular case, over here we have H2, and we have O2. Actually, we have 2 of those. And they're coming together, and the H2 is perfectly happy the way it is, and the O2 is perfectly happy the way it is. However, if you give them energy and you put them together and they whack into each other with the right amount of energy in the right orientation, then we create this thing up here called an activated complex. And that's when the oxygen molecules are essentially surrounded by hydrogen molecules. And what happens is they reform. Certain bonds break, certain bonds reform, and they form water molecules coming out the other side, which are the products. And when that happens, it gives off a lot of energy. So as these bonds are broken, that takes energy. So you're putting energy into the reaction, okay? And then once the new bonds form between the hydrogen and the oxygen, it gives off a bunch of energy. So the energy of our products minus the energy of the reactants, so the energy of the products minus the energy of the reactants gives us our delta H, which is the enthalpy of the reaction, which is right here, also called the energy released by the reaction. This is our delta H. Okay, so activation energy is how much energy it takes to make this thing start reacting. Okay, so if you only have a certain amount of energy up to here, they're not going to react. You have to have the full amount of energy all the way up to there. You have to put that amount of energy in before these things will react. So that's why, for example, there's hydrogen in our atmosphere, but the hydrogen doesn't react. It doesn't burn. Why not? It doesn't have enough energy to burn. Now what we can do is we can go and we can add a catalyst to the reaction. And a catalyst is a substance that increases the rate of reaction by lowering the activation energy barrier. The catalyst is not consumed in the reaction. That's very important. The catalyst is not consumed. It's still there, right? So if you think of your body, inside our stomachs, we have some digestive enzymes that help us digest food. If they weren't there, we would not be able to adequately digest the food to be able to get enough energy to live. So we have digestive enzymes in our systems that go and help us digest food. Those digestive enzymes are not consumed. They stay there. All right, so inside our bodies, they will go and they will help us digest the food, but then when the food is digested, the enzymes are still there. They haven't disappeared. You also have something in your car called the catalytic converter. So it's near your muffler and in the exhaust system of your car. So you have all these really bad chemicals coming out of your engine, and they come down and they go through the tailpipe, and they hit this catalytic converter. And the catalytic converter has some chemicals in it that convert some of those really nasty substances that would just go out into the air, and it converts them into non-nasty substances or less nasty substances that when they do go out into the air, they don't harm the environment as much. And that's what a catalyst does. Now, how in the world does it do that? Well, it lowers the activation energy. So in other words, if we think of the amount of energy it takes to convert those things to go through that reaction, it takes a lot of energy. But with a catalyst goes and reduces that amount of energy so it doesn't take that much energy to do that. So it's easier to go over this hill than it is for us to go over this big hill up here. And we show that with a rock in our previous podcast. Okay, so you'll notice the energy of the reactants and the energy of the products hasn't changed. So your delta H for either reaction remains the same. The only difference is how much energy it takes to get the reaction started. Okay, and that's important because if you have less energy to get the reaction started, it means the reaction can happen easier and faster. Now, there are things that work at the reverse of a catalyst, and these things are called inhibitors. And an inhibitor is simply a substance that interferes with the action of the catalyst. So reactions could slow down. They could even stop in the presence of an inhibitor. So, could this be used for dieting? Think of what would happen if we inhibited the catalyst from working in our bodies. Then all of a sudden, we didn't have, those enzymes wouldn't be working. They would not go and digest food. The food would come out the other end having been undigested, and as a result, you would not get as much energy from them, and your body would lose weight. All right, that's it. Go off and do the worksheet for this unit, and we'll see you in class. Ask us questions if you got them. See you soon. Bye-bye.